Okay,
Okay.
hello guys. Let's start with the lecture numbers and names number 6. Okay, can you hear me? How's your health, by the way? Are you okay? Vitya? Katya?
Yeah, I'm good. How's what, sorry?
Okay, good. They're good. Okay, we'll continue a little continue with some examples on symmetries, because symmetries is a very important thing in everywhere. Okay, let's talk about symmetries. If you remember when we talked yesterday, not yesterday, right? last time about symmetries, there are lots and lots of different symmetries in this world, right? Like for example, what we usually have in mathematics, like equals, like 1 equals 1. This is a symmetry too, right? Function, like we were talking about, like function f of x, where x is argument, is a symmetry where x is transformed into y. This is symmetry too. Yes, 1 equals 1, this is a symmetry. That's easy to understand, right? 1 is 1, right? But this is a symmetry too, believe it or not. And to understand why is it so, we should talk about first about some interesting things, which is called oppositions. Opposition 1 is the first opposition, is like reflection opposition that we talked before, right? Your face and reflection in the mirror, right? In the mirror, you oppose each other, right? So this is one of the form of opposition. This opposed to this, and this opposed to this, and this is a symmetry. This is easy to understand. Another opposition is like 1 equals 1. You can see it, they are opposed to each other, right? So that's opposition too, right? But there are some other oppositions which are not that easy to comprehend, but you should think about it. Like for example, black and white. Like white object and the same object but black. Or just the colors, white and black. Do they oppose each other?
Yeah, I guess so. No, it's a different object. It's like a different color now, so it would be different. But it is a reflection. Well, it's not the opposite.
No, just I pictured them like here, but like for example, it was one object which was white, and then whoops, it becomes black. Or whoops, it becomes white again.
It's different. It's different every time.
Still, the term opposition means that something opposed not only in space or maybe in time, right? It may be opposition in time too, right? Like you and you back 1 day ago, right? That's sort of opposition too, or reflection. But there may be other oppositions too, which are actually seems like oppositions, like white opposed to black. They are different, really different.
Yeah.
Okay, so if you think a little, you may understand that it's sort of a symmetry. And why it is a symmetry? Because something is still the same. In this transformation, when white is transformed to black, or black transformed into white, right? This is sort of a symmetry, and the same opposition too. So it's opposition and a symmetry. Why? Because something is really kept there. So other transformation, other symmetries, and we talked before, like a movement, right? There one object was here, then it moved here to another point, right? So which is of course the situation changed, right? Object was here and now it's here. It has changed, but still the object is still the same, right?
Yeah.
It moved, but it's still the same. The object where it used to be, now there's an empty space here, right? and here the object is occupying another empty space, which was empty before, and now it's occupied by the object, right? So something is changing, the occupation is changing, but the object is keeping the same. Same thing is like in white and black. Something is keeping the same, white and black. Now the other thing, the other example, which is called like opposite, which is called absence, right? Absence. Like imagine that we have some object, like some person, right? And then this person disappears. Not just is died or something, but it just went somewhere. We don't see. Okay? He goes through the door somewhere, and now there's nobody here. What do you think? Is this a symmetry or not?
No.
Is it an opposition?
I guess.
I think so. Opposition, yes, because here you are not absent, here you are absent, right? So there are no you or no this person in this place anymore, right? But still, you know that this person did not really disappear. It's somewhere, he is somewhere, right? He did not disappear totally.
Nor is opposition. That's the right word.
So yeah, it's actually symmetry because something is still kept. So the person is still there. It exists, or he exists. I don't know, he, she, whatever. So he exists, but just we don't see him for some reason. Maybe we just closed our eyes. Maybe he's still there. We just close our eyes. We don't see him, right? There are many ways how object can disappear from our sight, right? So the same thing is everywhere. It's not about only our side, but any measurement. You know, some measurement with certain scientific device. You know, it can measure something, and another measurement can show nothing. But it does not mean for sure that the thing that you're measuring disappeared, or it may just happen that maybe device is wrong, maybe something else. So many things are happening in these things, right? So another interesting example is called negation. Negation is a simple thing.
Oh.
You have some number like 1, right? And then you negate it. So you just multiply it by -1.
Oh.
So just adding minus.
Sounds like a negation.
Negation. So 1 is transformed to -1, right? So it looks like that you had something and now you have only that. You owe something to somebody, right? You have minus 1 fish, right? You had fish before, but you don't have it now. But this looks like an opposition. It's minus is opposed, like not having a fish is opposing situation to the situation that you have a fish, right? They're different, opposite situation. But is it actually symmetry? What do you think?
Oh yeah, one thing stays the same. It's still the number 1 except just negative.
All right, it's easy to see here. 1 is here as 1 is here, right? So still 1 as a unit is still there. We're still talking about a fish, and actually one fish, right? And we just put it into different circumstances, right? Right now we're talking that we have a fish. Right now that we have a dead on one fish. So, okay. So this is opposition, and this is a symmetry because something is kept. So, in general, we talked about this, but we can say it again because it's very important. Symmetry is a sort of a transformation. Symmetry is a transformation that keeps something unchanged. So when you talk about something and want to understand is it a symmetry or not, you should see something that is not changed. Something is transformed. Maybe lots of things are transformed, but something is still there. And if you think about it a little more, you will understand that for this definition, what symmetry are, many, I would say, almost all and every process in the world can be understood as a symmetry. It's just up to you. How do you talk about it? Do you talk about a symmetry or don't? So when it's something that unchanged is very obvious, it's easy to see, right? Reflection in the mirror, right? It's easy to see that it's a symmetry. Something is not that easy, like a black and white. Some questions, right? What is still there in black and white, right? For example, negation, maybe easy. So let's keep in mind that this transformation that keeps something unchanged. What can be unchanged? -1, 1, many things. I will repeat a little. I will repeat it again. Like in physics, these symmetries are actually the main thing, the most really important thing that physics taking care of, right? Symmetries, like for example, symmetries, when we talk in physics, there are two great symmetries. Symmetries which are connected with transition in time. So you just have the same situation, but you move it in time, like from one point in time to another point of time. If the time is similar in all places, that we may take it as a law or whatever, so time is not dependent on anything, like for example, then the situation would not change if we look at time at the other point of time. In general, it would not change. It may change in some details, but in general it doesn't mean anything for the nature if you change time from one point to another. If you take this as a law, you immediately comes to one of the greatest law in physics. It is called energy preservation. Energy preservation. Energy preservation means that energy, which you heard of, what is energy, right?
Matter?
Energy is preserved, so it is kept unchanged. Whatever you do, energy is still the same. Like for example, you can hear like that for example, that car runs on fuel energy that kept in the gas, right? Fuel energy, right? The fact is, yes, its energy, this energy is used, but it does not disappear anywhere. It's still there. Energy still the same. In any process in the world, energy is still the same. It's kept unchanged, and it is connected with the symmetry. Believe it or not, but it's connected with the symmetry of time, transition in time, and this is proved in physics, in modern physics. Another transition is transition in space. The same thing, space, yes, space. So the same thing, we just change from one point of space to another point of space. If the space is similar everywhere, we can take it. We'll find out another great law. It is called momentum preservation.
Atom preservation?
Momentum. So something, the physical thing, momentum is actually the mass of the object multiplied by the speed of the object. This is momentum. That's a simple thing, but anyway. I just get it as an example. There are two great laws of physics: preservation of energy and preservation of momentum. They are connected with the transitions in time and transition in space. Just for you to understand, it's very important to understand. And this is all connected with the symmetries, right? we'll talk with different type of interesting symmetries. You at least you don't know exactly what formal logic is, but you heard about logical things that is called, maybe it's called syllogisms.
Heard that.
It's a very simple thing. It is actually when we talk like this: if something happens, if, then
A code.
then something other happens. If A happens, B happens. Then, right? Or usually it says like, if A something is true, then B is true. This is, you may say, hence, or if then, or this is called syllogism. So this, if A is true, B is true. The same thing in physics, it is called causality. So this B is, A is a cause of B. B is caused by A. So if A happens, then B happens. And this is called causality, which is a very important thing in physics.
So B is caused by A?
Yeah, B is caused by A, yes. In logic, it sounds like this: if A, then B. In physics, it's called causality. So some event A causes like event B. These things are very much connected. And if you look at this, it looks like very much like what?
If symmetry.
Symmetry, right. Symmetry. And what is kept here? What is kept in this type of symmetry?
The A.
No, A transformed to B.
True.
Huh?
The true part. If
True?
A is
True part, yes. Or it is another called is truth, right? Truth. Maybe truth or false, right? But here is truth is kept. So again, this is the logical syllogism can be called the preservation of truth law. Preservation of truth. Other symmetries. The same great guy, which theorem you know very well, Pythagoras, right? Who lived about 500 before Christ, 500 years before Christ. The same guy, he also discovered interesting things. He discovered laws of music. I think I told you something about it, no? Or maybe not. Not? Okay.
No.
Okay, so this is the guy who actually discovered the laws of music. And he discovered in a pretty interesting way. And they are connected, of course, with our theme, as you understand, right? So, for example, in each musical instrument, like guitar, or piano, or grand piano, or whatever, right? We have their strings, right? String is something like a string, right? Metal string usually, that is placed between two fixes, right? Here and here it is fixed, and it's stretched as a straight line, right? Now, if you pull the string, what will happen? The string will like pull down, for example.
It'll go back up. It'll collapse.
Yeah, of course. Yeah, of course. So if you pull, it goes like this, right? And then it goes back like this, right? And this will be, scientifically speaking, oscillating or vibrating, right? in this way, because these 2 points are fixed, right? They are not vibrating, right? Vibrating only the center, right?
Yeah.
Now, if you pull it not in the center but in some other place, like here, the other things will happen. A little more interesting. Not only this, they call it's called mode of vibration, right? Vibration mode, or the other term is oscillation.
Oscillation. I did it in my
Vibration. So if you see the center here, it may happen this way. The string, which was like this, which was like this, it may vibrate like this.
Oh wow.
So this point is fixed again. You may actually, when it vibrates like this, you may put your finger here and there will be no vibration. Nothing will change. Will be changed because this point is not moving anyway. The moving are these parts, and this point is not moving.
Oh wow.
So you may do another thing. Not only this mode. This is like mode 1, right? This is mode 2. There are also mode 3, like this. So you see here 1, 2, 3, 4 fixed points, right? And vibration goes like this, here, here, and here. If you pick and pull any string somewhere here, not in the center but somewhere here, all these modes will be in life. All the string will vibrate this way, and this way, and maybe some other ways. Yeah, and the tones that are produced by these things, they produce different tones. They have frequencies like simple numbers. 1, then 2, then 3, and else. So simple numbers. Simple and small numbers. That's what Pythagoras actually discovered. That the string oscillates in these modes. Not 1.5, not 1 and the 27, whatever. 1, 2, 3, 4. Simple numbers.
What do you mean the numbers?
The numbers is like, this is 1. This is 1.
Is it the number of peaks?
Yeah, you must say, no, not number of peaks. You may count also like this. Here, no fixing points. There's 1 fixing point. There are 2 fixing points like this, right?
So the top one, is it going to be 1?
But it may be 0. If you count by the fixing points, it will be 0, right? This will be 1, this will be 2, and whatever. But actually 1, 2, 3, and 4, this is usually called number 1 because this is a frequency. The frequency number of oscillations in a second. So oscillations, number of the vibration. Vibrations per second. This is called frequency. Frequency. So the frequencies are related like this. Frequency 1, then it's doubled, then it's tripled, then it's 4 times more, like this. So the frequencies relates like 1, 2, and 3, and 4, and more.
But what happens if we pinch the string at some really odd place? Here in your example, you pinch the half, a quarter, and what if it's some odd like
the oddest thing if you pinch it like here, very close to the fixation point, or here, right? Because if you pitch it, pull it right here, pitch here, right, it will be only mode 1, and that's it.
Yeah.
If you the more close you come into here, the more modes you have. There are more numbers here. More and more numbers. Like if you come close to this, will be maybe 1 and 2, close but not exactly in the center, right? It will be modes 1 or 2 maybe. If you move there, more and more and more and more.
Is that one of Pythagoras's
discoveries?
Yeah, yeah, it was his discovery, yeah.
But a question:
yeah.
Is there a formula that connects the number with how far from the end of the string you pinch it?
No, that's physical, of course. In physics, there are all kind of formulas. Of course, there is such formula. You can, but if you try the guitar, just a sec. If you try the guitar and you try to pitch it closer to the end, any string, right? You will see that it will become more and more metallic sound. The sound will be, in general, will be the same, right? Because this frequency exists anyway here, the main frequency. But when you pitch it here, it sounds very metallic. It means that there are many other modes are there.
Okay.
More rude. Yeah. Okay.
But the formula to give you the number should always return an integer, right?
Yes. The interesting thing that he discovered actually is that whatever you do, there'll still be integers.
So that's my question. Like, how can a formula always return an integer? How is it done?
No, that's a long explanation. Actually, it's not easy. Not easy to say it right away. No.
Yeah, because like I said, you're halving it every time, so that's clear. But what if you just did some, not halved it, but divided it by pi? Some really weird place. Like, well, what it would still have to be an integer. Anyway, if it's too much, it's okay.
Yeah.
Okay.
Integer. There is a way how to get I understand your questions. How to get integers out of non-irrational numbers, right? Yes, but there is a way to it, and it's connected. But believe it or not, it connects with symmetry theory too. It's symmetry theory. This called the term is just how to write eigen values. Eigenvalues and eigenvectors. This is the term, but to explain it is a little more difficult. So it's the same as mode actually. So it's
I remember that actually.
Yeah. Okay. So now now these tones discovered by Pythagoras, right? Pythagoras?
Yeah.
Pythagoras, okay. They lead to a modern music, modern laws of music, actually. And how it is, it's very interesting. If you take the piano keypad, right? So there's a thing that is called octave. Octave, right? So octave is a so-called musical interval between.
he's ahead or behind.
Yeah.
Like from note, each note. Give me some note. Huh?
C to C. C to C.
C, yeah, C to C, and C from like first octave to the C of second octave, right? Or C third octave. So the frequencies of this are exactly like this. Yes, the C of the prime octave, what's the term of this? The first octave, and the frequency of the second octave relates like 1 and 2, and 3 is like a 3. So these are octaves. They are exactly that strings that we saw in the previous picture. C1, C2, C3. All the rest notes actually, they go with division like 1, 2, 3. They divided by 2, divided by 3, divided by 4. something like this. So and they get between them, in the interval between two octaves, you have separate notes, right?
But how does a C and D relate?
No, that's again, I would not explain this, but it just because of this division, like 2, 3, and then, right? The notes are separated by so-called musical intervals, right? And the intervals are the same, and they are displayed on the note, how you call notepad, note.
Musical notes.
Yeah. Okay. So you here or here or here or here or here or here, right? Like here, another note here, here, and up to there, right? So up and up and up. All of them are related like this, but in here between them, it's not already integer numbers, but they're divided into equal parts, something like this. So that's how is organized the notes organized. The same thing is not only in frequencies of notes. These are frequencies, right? Or sometimes they call tones, right? Tones the same as frequency. The other thing is with the durations. Again, there is a whole note, right? Who know this? The notes, they know the whole notes is denoted like this, right? Like a circle. Then there is
quarter note.
Half note.
Quarter.
Like this, right?
Yes.
Then is.
That's a half.
That's a half. Then is.
Gotcha. Now that's a quarter.
That's a quarter. So this is 1. This is divided by 2. This is divided by 2 again. So it's 4. And now.
I was telling you this. It does. That's the half. Yes.
That's half again, right? That's 8, right? So again, it's divided by 2 by 2 by 2. So you see the whole things here are organized again by numbers. So this is one of the other examples in music, right? And again, this is if you look at it, it looks like very much like symmetry. These are symmetries. If you transform one note into another, it will be different frequency, right? But still the sound is preserved, and also some other things are preserved there too. Now another example of symmetry is very important is language. To understand language, first of all, we should talk about intonations. What is intonations? Again, if you pronounce something higher tone or lower tone, or some changes in these tones. The intonation actually it is music. Actually music was called art of intonation.
Really?
Yes. For dozens and dozens of years it's called art of intonation. So our intonation gives birth to music, actually. Music starts from this, and we use special instruments for this. But we may sing too, so we use our voice as an instrument, right? So music of intonation. Then it is rhythm. And rhythm is what? It's going one after another, after another, after another. And this interval may be shorter. Again, they divide it into 2, so here, or longer, like this. And again, there are integers. The relations are integer. Rhythm. The same thing is in poetry now. It is called rhyme. Wrinkle. What is wrinkle, wrinkle, little star, right?
Yeah, song.
How I wonder what you
Are.
This is rhyme. And also in language we have things that are called phonemes or vocal letters in short. It's not exactly like this, but it's easy to say. Vocal sounds like A, O, right? Like U, whatever. So these sounds, believe it or not, they are constructed as musical chords.
Chords?
Chords, right? Musical chords. And musical chords are constructed exactly like Pythagoras discovered. Their frequencies are related like 1 to 2 to 3 and something like this.
So no, but this contradicts what you said before, because you said before that it is the octaves that relate to each other as 1, 2, 3.
Yeah,
and chords are not.
I was about to say.
No, that's a little more. I agree. That's a little more complex there, but the chords are not as simple as octave. You know, chords are not octave relations, not like that. But the main law in it is still that. The main law that lays under all that, right? So it's just I cannot go into all music theory. There are lots of things there, but this is the law that lays under all these ideas. So believe it or not, these sounds are chords of certain size. O is the most harmonic. O is the most harmonic chord. R is, I would say, pretty much disharmonic. I forgot what's the term in English for that.
Rock?
No, when there's no harmonies. It's when you play all McDonald.
Yeah, there is a harmony, but the harmony is very, like if in O relations are 1 to 3, in A relations are like like 1 to 7. So that's more. It's far from the main sound. It's further related than this 2 and 3, like 7 or maybe 12, something like this. So phonemes sound like this, right? And in the language, we may talk about again transformations like A to O, or O to A, right? Like A to like U or back, and so forth. We may talk also about other symmetries like syllables, like Ma transforms to Ma.
Wait, it didn't transform. Wait, no, it did. It moved from one to another. Oh, yeah.
And if Ma transforms to Ma, in the process, how would it sound?
Transition.
Yeah, transition. Ma and then?
Ma. Mama.
Yeah. Now we have the word. And something else. Okay? So I hope that I gave enough examples in that, right? I have still maybe 5 minutes. I'll explain something a little more about it, and then the questions, right? So okay, we talked about things that we call paradoxes, right? Remember paradox, liar paradox?
Yeah.
So liar, when he says I lie, right? So the question is it true or false?
Both.
So liar paradox actually transforms, you may say that it transforms true to false. And back, if it's false, transforms to true. So this, right? It does not keep true. Remember the logical syllogism, it keeps true, right? Truth. It's preserved truth. But here, truth is not preserved. So the first question is about the paradox, because paradox exists, right? The paradox of liar is a pretty existing thing.
Yeah.
So the first question is like this. What is actually preserved in paradoxes liar and some other paradoxes that you can invent yourself, or I'll tell you just in short. So the first, what is preserved here? Definitely true. It looks like it's not preserving, but what is preserved here?
Transition itself.
It is guys. You may talk. Okay, you may talk later. Okay, this is the question. Okay.
Okay.
Question number one. Question number two. No, this is still for question number one. Another paradox, like paradox of nothing. Pretty well known in philosophy, right? So if we have absolute something like we call absolute nothing, right? So logically speaking, if we have absolute nothing, nothing at all, right? So there's no nothing too.
It's nothing.
You understand what I'm saying?
Yeah, yeah.
If we have absolute nothing, there is no nothing too. But if there's no nothing, there should be something. Or actually everything, anything. And if you look into anything, absolute anything, so you may find there whatever you want, including nothing. Why not? And if you find nothing here, we return back to absolute nothing. So this is a paradox too, and so the question is still the same. What is kept here? It looks like a symmetry. Is there something preserved or not, or what preserved? Okay. Okay, the second question.
The transition that's preserved.
Okay, you may talk. Second question: what can you find out other symmetries in language? Just think about it. What other symmetries can you find in language?
It's like bump and then I say mug. Ow. That's not peaceful.
So examples in language, right?
Can you give us examples?
No. I gave you something, right? Phonemes, remember? Syllables. Find other symmetries in language.
Okay.
Or maybe if you want, would be nice if you think about other symmetries anywhere. It's just up to you, right? Do you have time for that? It's pretty maybe big question. And also there's a question 3. Question 3 is connected with some interesting phrase, or you may say formula, philosophical formula, which belongs to famous philosopher, George. Oh Jesus, it's not really George Hegel. And he said once that each nothing, you may write it if you want, each nothing
Something.
is always
Something.
particular nothing of
Something.
particular
Something. Nothing.
something.
Oh, something. Yeah.
Okay, I just love this thing. It sounds like mathematical formula. Just each nothing is always particular nothing of particular something.
That's a paradox. Yeah.
Well, no, I guess that's when you say nothing, you just mean this nothing is applied to something. Like what's going on?
Wait,
Nothing.
I have a paradox.
It doesn't mean that there's no air.
Okay, guys, I want to explain. I want to explain. Like zero is nothing of a number.
Yeah.
Can I tell you what paradox I made up?
Black is nothing over light, right? No light is black. and something like this. Like pause, okay, pause is nothing of sound, or of speech,
Pause. Silence.
Pause. No sound. No sound, pause. No light, you know, black, dark. Black, dark, you mean darkness, right? Darkness. Okay. So, and this is means actually exactly that. So, whenever you talk about absence of something, absence, right? Absence. It's always some particular absence, like absence of light, absence of sound, absence of everything, and whatever else. So the question is, give some more examples of particular nothing.
What's wrong?
Nothing.
All right. Exactly.
This is the paradox. So it says yes equals no, and then someone asks them, do you want to jump off a cliff? They say no. What do they mean? Yes. No, Patch, but yes also equals no, so we can equal no, but that equals yes. That means no equals yes.
And finishing, I'm sorry, I forgot one small thing to say. One small thing to say, just to think about some paradox too. Paradox, right? So you have a border, right? A border between something 1 and something 2. A border. So what does this border do? It separates 1 from 2, right?
Yeah.
Separates. But does it unite them too?
What do you mean? Wait, did what did you say?
Connect them. Does it connect them too?
They connect, unify.
No, it keeps them away.
This is the border. It's obviously it separates 1 from 2, right?
Yes.
But also it connects too. Like for example, you have a river that separates two states, right? Or kingdoms.
Yes.
Kingdom 1 and King 2. They are separated by river, but they are also connected by river too. So this is a sort of a paradox. Just think about it. It's an important thing to understand.
Look, Canada and America, they're also connected because, like,
No, but think about like a door. It separates the hallway and the room.
But it's states connected.
But when to get from the room to the hallway, you have to walk through the door.
Great.
And if you destroy the door,
Great example. Door. What does door do? It separates the rooms and also it connects the room.
Door do.
Door to.
That's pretty cool.
Okay. So that's it, guys. Any questions on this? Except I gave you my questions. Any questions?
No.
Give that your.
See that?
Oh.
I have a paradox.
Okay.
You say yes equals no, then someone asks you, do you want to jump off a cliff? You say no. What do you mean?
Say it again. Yes and no. If you jump from the cliff.
No, did someone says yes equals no.
Did I say that?
No, someone says yes equals no. Then they ask you, do you want to jump off a cliff? You say no. What do you mean? Yes or no?
Yes, right. It equals. If it equals, it may mean whatever.
Yeah.
There's interesting, actually theory, not theory, but it's a theory that accepted everywhere right now for 100 years already. It confirmed experimentally. It's called quantum mechanics. In quantum mechanics, there is no thing like true which is true. It's also, if it's true, it may be false. At the same time, there are only chances there. If you remember chances, the theory of probability, there are only chances. You may talk and calculate only chances, like 30% that this is true, 70% that it is false, or something else. So it's true and false at the same time. You never can tell exactly. So it's not only about just talking and questioning, it's also about like very serious experimenting in physics. Okay?
Yeah,
Okay, guys. Stay good. We'll see you soon. Okay.
okay.
Thank you, guys.
День рождения Нади, напомню.
Guys, tomorrow is Natya's